All right, good afternoon, everyone. So welcome back to another sessions for the deep learning and PyTorch. Okay, I believe today we're going to visit a new topic, which is going to be, I guess, if you haven't tried this before, this will be the first time for you to do some actual machine learning. I mean, I guess you have done it with Ajahn Vimalin, but this is going to be the deep learning with PyTorch, I guess, if you haven't tried it before. Today, we're going to actually do some actual machine learning. Okay, so let's get to it. Okay, in case you're wondering, it's going to be this one. This will be the link. Is it? I'm actually not sure. Let me check. Yep, okay. So that's the link. Okay, and today we're gonna visit this code. Okay, so why don't we download it and put it in your usual location of choice. Okay, again, we'll have the zip file, so don't forget to extract it into your preferred location. And for that, I will just put it in this folder right here. So this is my folder. So I want to do MLP, right? Okay. 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 So just two files, but actually there's a lot to unpack in here. So we're gonna spend today, hopefully finishing the two tasks, which is regressions and also classification, okay? And I think it might be a good idea to try to run the first cell as usual. So if you have a chance, right, just open S01, see if you can run it, right, just to make sure. For me, I think I would just have to do another folder. I have to do this one. Okay. Okay, so and also if you're interested today, I will be using the diagram. Okay, not this one. From here, okay? So if anybody interested, you can take a look in more details, or you can just follow with me on here. Okay, I want the themes, appearance. Okay, I like the dark themes, okay. Okay, so basically we're going to go through this workflow, which is machine learning workflow, and I mean you're gonna see that it's quite similar to how you would do it in another software, because the software is just a tool, but usually we do the same thing, just everything's in Python, so it's a bit more, I guess, it's a bit more unorthodox for if you're coming from like software with mouse, so we just have to type everything in the commands, that's all. Okay, so let me get started, okay? In case but if you want me to go debug your laptop, please do so. Please stop me, okay? Mm-hmm.
Because it was long, it was like 16 seconds, and it was just random.
It's gonna, okay, yeah, take some time. Okay. All right, so first of all, let's check out our workflow, okay? So we're going to start with regressions, which is we're going to predict a continuous value, okay? And next, we're going to do classification, which is to predict, actually, it's for classification, we are predicting values too, but the value is the label. It's not really decimal, it's just predicting, 1, 2, 3, 4, it's a class label. It's not really meaningful in terms of like physical meaning, but regression is actually the continuous values, okay? So first we're gonna find some way to load the data, and this one, your data can come from anywhere, but today I'm gonna use the toy data that every machine learning practitioner uses at the, during their first, at the beginning. This is gonna come from another library called scikit-learn, okay? And I haven't told you about the scikit-learn at all, but we are going to use it just for data and utility, okay? So as you might notice that the import parts actually import something from scikit-learn, okay? Right here. Let me just run to see if mine's working too, okay? Wait, where's wait, it's gone, okay, whatever. I'll just leave this on for a bit in case you need it, okay? All right, so let me select my kernel. I think this one, and that. Okay, so looking at the imports, okay, I'll just close this one. First, you have Panda, just for data processing, just regular data processing. Seaborn is for plotting. Okay, you haven't seen me use it too much, but you will today, hopefully. And then Torch is something that we tackled last time. Maybe, I don't remember the last time and the week earlier. And also the new one that I haven't mentioned at all is called sklearn. It's called scikit-learn. Okay, so let me show you kind of like the website, sklearn. Okay, so that is the premier, actually another very popular machine learning library for Python. But this one focuses very heavily on the classical machine learning. So any of the methods that you did with Ajahn Vimalin through the software, this one has it all. Okay. It's so popular that actually the syntax that other libraries are actually copying this one. Okay, so like the name of the function, the name of the variable, some of them it's actually inspired by this library. So this one is more like the original, kind of the biggest original one. Okay, and I still use it, you know, very frequently. You know, I use it for doing classical machine learning. But when it comes to deep learning and, you know, neural nets, I think PyTorch is a king. So that's why we're learning PyTorch, because for us it's a deep learning part, right? But even that, you know, I'm still using scikit-learn just for the utility. For that alone, I think it's very good library. Okay, so we're going to use it just for the data and utility. So the first thing that we're going to do is this one. So scikit-learn comes with the toy data. That most of the machine learning people use it for just prototyping something, okay? And we're going to use that. So first we're going to load the data. And the syntax or the code that I'm using right now, it just, you know, very specific to scikit-learn. It's not standard or anything, you know. So scikit-learn come with the function. This is a function called load diabetes, which is called the diabetes data. Okay, so I'm going to say load diabetes, okay? And because it's a function, so I need to call it like this. If I were to just run this one, you're gonna see that it's actually outputting actually the data itself, okay? Although the data in here is actually kind of packaged into the dictionary. So I'm gonna save or store this data into a variable called diabetes, okay? Basically just storing the results of the function call, okay? And the first thing that I can do is, you know, because I already know the shape of my data, so I can call, for example, I can print diabetes.descr, okay? And all of this, again, not standard or anything. You just have to look it up, the documentation of what's available, okay? So this one, it allows me to print the description of what the data is. So you can kind of go through it. So it's a diabetes data set, okay? And it has the variable, the features or X variable as follows. And also the Y variable is called the target, okay? So the target is the column that is the measure quantitative measure of disease progression 1 year after baseline. So, I mean, it's not kind of important here, but it's good to know, what kind of data you're working on and what is the meaning of what you're predicting, okay? Although for me, for you, right now, it's just a number, right? But yeah, we're predicting something that has to do with the progression measure of the diabetes, okay? So let's check out the actual data, shall we? So the data is designed so that I can just put it into Panda data frame very, very conveniently, okay? So the raw data actually looks like this, diabetes.data. Again, all of this, I just need to look it up from the documentation. Nothing standard about this, okay? These are the data, okay? And you can see that there are, you can see the shape. So the shape is 442 rows and 10 columns. So that one is the X value. So you can imagine that right now I have my X, let's say X1 to X10, right? And then I have observation, 442 observation, meaning I collect information from 442 persons, basically. Okay. And then there's also the target. Target is the Y variable, the things that we want to predict. Okay, so diabetes dot target. Okay, again, the target is the number, right? And again, the meaning of it, you can read it from the description, but it's just one column basically. Okay, so you are collecting 10 information in order to predict one value. I guess that's what your model is going to do, although it can do multiple predictions at the same time, and that's the number of the rows that you can put it in, okay? All right, so looking at the data like this is kind of hard to get, a grasp, right? So I usually put it into the Panda data frame. That actually allows me to do some, initial data exploratory analysis, okay? It's very, very easy to do. So let me show you. So I'm going to put all of this in Panda data frame. Again, Panda is also premier tools when you have tabulated data like this, okay? So I'm going to say data equal diabetes.data. That's my X value, okay? And then I'm going to have columns, okay? So this diabetes variable also contains the name of the columns. It's called diabetes.feature name. Again, this one I know from looking at the documentation. I don't know this. It's not standard. Again, okay. And if you just run this one, you can see that now it makes more sense to see the data in a tabulated form like this, right? So you can see that there are 10 X value basically, and then we're going to predict that progression of diabetes in terms of the number, okay? It might be kind of nice to actually include, so right now I have 10 columns, which is the X data. It might be kind of nice to append the Y value at the end. Usually that's what you typically see in the Excel. So I can just do that too. So I'm going to store this one in DF, which is data frame, right? And then I'm going to say the last column is going to be called target, okay? It's going to be equal to diabetes.target. Okay, and if I were to just look at it one more time, you're going to see that now I have my target. So again, what we're doing in terms of model prediction is if you give the model 10 value, it's going to split out the target value, right? So that's the gist of the prediction model. Okay, and again, the number of row, which is the number of observation or the number of prediction that you want to make. Okay. Okay, so let me show you that once you put things into Panda, it's very easy to do data exploratory analysis. For example, histogram is something that you might be interested. So hist, okay, there you go, right? And then make more sense to get a look at all of the data in here, right? Again, I'm plotting the histogram of all the columns, including the target, right? So there are X and Y. So the purpose of the histogram is actually give you a visual indicator of whether you actually collect the data correctly or not. Things that you want to kind of look for is like if you have outlier. If you have something that appear very, very far away from the groups, then maybe you do something wrong with the data. So that's good visual indicator, right? The histogram is a bit cramped, so I can input some options for to make it look a little bit nicer. So bin equal 20, and I want the figure size to be larger, so 12, 10. So 12 inches in width and 10 in, sorry, actually 12 in, so 12 in width and 10 in height. I think it's width and height. So with that, then the histogram looks nicer to look at, right? And again, you can see that for sex, it's a bit kind of strange, right? Because we have a number representing sex from negative to positive. So you can imagine it's like a male and female, but you encode it in terms of a number, right? So that's not unusual, okay? But for the categorical variable, we need to do something about it. For example, split into two value like this. Some people call it one-hot encoding. You can call it whatever you want, okay? And for me, this data is already standard, so I'm pretty sure there's no problem with it, right? Another thing that you might want to do is, whenever you're building a model, it might be good to see some correlation, okay? So correlation means that if there is increasing in X, do you see increasing in Y or vice versa? Okay, and as correlation increases, you can expect your model to perform better, okay? If you have data that has no correlation from X and Y, then, deep learning is not going to help you, okay? You're not going to be able to fit anything to it, okay? So first, check correlation to see if your data actually can be modeled, okay? And correlation can be visualized very easily by using df, which is the data frame, right? .corr. So that's going to calculate the correlation matrix, okay? Again, the correlation matrix just tells you the correlation between different variable based on rows and column, right? So what I'm looking for is actually, I want to see my target. And I want to check if, do I see any correlation of the target and the predictor or the features? If it's all zero, you can pretty sure that nothing's going to help you build a good model. Like you can just, go back and collect more data, but your data is unusable. Okay, so that's a good way to do, right? Before attempting to do anything, just make sure your data has some trend or has some useful signal on it, right? And sometimes looking at it like this might not be, as easy to look at. So a good way is to do the heat map. And also this one, Seaborn, which is the plotting library, has a very, very easy method called heat map. Okay, so sns.heatmap. I'm going to input the correlation matrix. Okay, so I have to store this in my memory, so core matrix, okay? And then I'm just gonna display it here. But then I'm also gonna put the correlation matrix in my heat map. And this looks a little much nicer, right? I'm not too much concerned about correlation amongst the features, although actually, if you are trying to figure out the variable importance, actually this matter, okay? It's called the multi-collinearity effects. But then if you just want to do prediction, it's fine, okay? But what I'm very interested is actually this guys over here, or actually this guy over here. There are symmetrics, okay? You can look at the row or the column, doesn't matter, okay? But what you want to look at is actually the magnitude of the correlation, okay? It can be positive or negative. It's okay. As long as you get some non-zero magnitude, I think you should be good to go, okay? For example, I'm looking for something that's, relatively red, because red, mean it's a high correlation. And you can imagine that, I do see some, pretty high correlation, maybe even BMI. So I guess The closer to white, the higher the correlation if you look at the color bar, okay? So, you know, not this one, okay? Because this one is always 1. You know, correlation to yourself is 1. But then I want to see, so BMI, S5, you know, and maybe BP or S4. So I do have some useful signal I can use. So that means that I think, you know, I can make a pretty good model out of this. And, you know, if you have a good correlation between your features and your target variable, sometimes you don't even need deep learning. You just use like a normal classical machine learning and you're good to go, okay? So do not underestimate classical machine learning. I always emphasize this because we always drawn by like all the hype, all the you know, flashy things that comes up, you know, at the latest time. But you know, sometimes the classical things good too. Okay. All right. And another thing I want to show you is I want to show you the magnitude of you know, of the variable. Okay. So I'm going to do this one, box plot. Okay. df. Okay. Dot. So right now I want to do ilog, meaning that I want to select the first 11 columns. Okay, so that's all the x values. So I'm going to choose all the column, and I want to go from the beginning to the end, except the last one. So this one is the way to select all the columns except the last one. Okay, you have to take my word for it. Like we went through this a long time ago. I don't expect you to remember this, but trust me, this one, select all the column except the last one, okay? But what I want to do is I want to dot box plot and check this one out, right? So essentially, this one tells you that the data is, all the x data actually lies in the same range, okay? No matter what it is, pretty much everything is actually in the same range, which is very good. This is what we want. Okay, we want the data to have the same magnitude because or else, you know, you're going to have some unintended consequence where some of the feature dominates the prediction, even though it's just a matter of scaling. You don't want the scaling to be important to have effects in your prediction. Okay, and up to here, I think that I made one, I omit one important option. So let me go back. Okay? For you, it might look different because you know what? I forgot this option when I was loading the data. When I load the data, I think in my solution, I have scale equal to false. If you have that, that's good. So you follow the example. But if you follow me, actually I forgot this option because this one is intentional. I want to show you what happened when you have the data that is actually unscaled. And that's more common, right? When you collect the data, usually it's not scaled. And this one, I think it's going to make more sense to you, okay? For example, right now, the age goes from 20 to 80. Yeah, makes sense, right? Sex, it's just a categorical one-hot encoding. So this one is just 1 and 2, basically. So 1 for male or female, I'm not sure, but usually they just do 2 number if you have a categorical number. And then the rest is, you know, I don't know the range, but I guess BMI, I don't know, maybe something like 20 to 40 sounds okay. The rest, I don't know if the range is right or not, but as you can see that when I choose the option where the data is unscaled, this one, right? The range actually become much more different, right? You have something that goes from like 100, and then one that goes from 1 to 2, and then the other one goes from 1 to 6, right? That is some typical things that you probably is going to encounter when you import your data from observation, okay? But again, you can, no matter the scale, it doesn't affect the correlation. The correlation is already scaled, so already get rid of all the scales. So it doesn't matter if you have scaled or unscaled data. The correlation is the same, okay? But what's going to be different is when you do box plot like this, okay? You're going to see that some of the variables have large range, the other one small range. And this is going to be a problem if you put this into your neural net training, because then what's going to happen is S1 is going to dominate the prediction, which is kind of artificial because I can always scale the data by different units, and I don't think that should affect your prediction. Okay, so what we are going to do is we're going to come back to here, and okay, so I forgot to tell you that once we load the data, usually we explore the data. Okay, and we're gonna do data extraction. Okay, so data extraction is just a way to just kind of put things into a more like a typical pattern that I usually do, which is X and Y. Okay, so right now we have data frame, right? But in the end, when I'm going to do machine learning, I usually just do X and Y. Like, what is my X? What is my Y? So that's, to me, I name it data extraction. Okay. All right. So let's check it out. So it just as simply as just extract the target from the data frame. Okay. To do that, I want to do df.ilogged. Again, I want to select all the columns except the last one. That's going to be my X. Okay, my X. Okay. Okay, and then so this like that. Okay. Trust me, this is all the column except the last one. Okay. I'm going to input it into underscore X. Okay. So whenever I'm starting to do machine learning, X and Y makes the most sense for me. So I do X and Y. Okay. And then I'm going to do dot value. Okay, so dot value means that convert the X and Y into NumPy array. So a more primitive data type. Okay, although you can stay with data frame, should be fine. But I usually just, like before I do machine learning, I want the data to be in the right type, which is NumPy array. I think that's the most common, I would say. Okay, so next I would do Y equal df.ilog. Okay, and then I just want to do this one. Okay, so that means that I'm selecting the last column. Okay, dot value. I think value with S too. Sorry. Okay, all right. So if I were to run this, right, and then I just kind of see what X and Y. Again, I do underscore X and Y. Okay, this is intentional. Okay, I usually name things in a certain way so that when I see the variable, I know kind of what it is. You'll see later. Okay, so if I check my X, then you can see that it's a NumPy array. Okay, with 442 rows and 10 columns. Okay, and then my Y, which is underscore Y, right? It's going to be another. Okay, let me just do dot shape, easier. Okay, it's going to be a value with 442 row, same thing, but one column because I only predict one thing. Okay, that's my intention. That's what I'm doing here. So data extraction. Okay. Okay, so usually I just do like print X underscore X dot shape, and I want to print underscore Y dot shape just to make sure that I got the size of the array that I want. Okay. All right, so data extraction. Okay. Next up, okay, so I'm going to split the data. Again, I'm pretty sure Ajahn Vimalin told you about this, right? When we do machine learning, we want to split the data into training and testing. Although if you go even further, actually you want to do 3 types of data. There would be a validation set, but we're not going to cover it here. Okay, but again, just for the purpose of demonstration, okay, train and test would be suffice here. Okay, but for real production or real academic run, I think you need to have 3 data sets called validation and test and train. Okay, so just to make sure that you are aware that what we're doing here is actually a little bit, I guess, biased. What that would be the word. Okay, all right. So I'm going to split into test and train. Okay, and again, if you want to write the way you want to write an algorithm to do it yourself, it's up to you. Okay, but this is when scikit-learn is really useful because I'm going to use the utility function called train test split from this library because this library is super useful, super popular. Okay, so this is going to be from here, this one right here, train test split. Okay, so I'm going to borrow this particular functionality from the scikit-learn. Okay. Okay, so the syntax is train test split. Okay, and inside you can give it your data. Okay, so I'm going to underscore x underscore y. So I want to split x and y into two sets. Okay, and when I say split, I mean split by row. Okay, we're not split by column like rows. Okay, and then all you have to do is just tell it that I want the test types to be 0.3, meaning that I want 30% of my data or rows to be in the test data, and then 70% to be in the train data. So usually, 0.2, 0.3, 0.1, pretty standard. Okay. And then I can also do random state. Okay, so random state is just a way to control the randomness of the split. So if you say random state equal to 0, it's going to split the same way every time. If you don't do random states, then every time you run it, it's going to split differently, meaning pick the different choices of rows into the train and the test data differently. So if you all use the same random state as me, you are going to have the same sets of training and test data with as similar to what I have too. So it would be so I normally do it with 0 or something. So it doesn't hurt to do. Okay. Okay. And right now, what you're getting from here is a lot of things. Okay. You're going to have 4 things as the output. Okay. And that 4 things is going to be contained in a list. Okay. So usually, if you have something that come out as a list, people usually just write in a syntax that's shortest as possible. And the way that we would kind of, peel apart the things in the list and put into the new variable is called destructuring. Okay, we're going to destructure the list. So we're going to do underscore x train. Okay. So the first thing in the list is going to be x train. So I name it underscore x train. The next thing is going to be the test data in x. So underscore x test. Okay. Again, all of this I have to look it up. Okay. Nothing standard about it. Okay. The next thing is going to be the y train. Okay. So the y data train. And then it's going to be y test. There you go. Okay. Again, the reason that I have to do this, is that usually when you run this function, you get 4 things in a list. But I want the 4 things inside to have a different name so that I can just store it in, with my variable. So this technique is called destructuring. So I'm destructuring the things in the list and put it back into this particular variable in this order too. Okay, so if you inspect your variable, then you should just see all of this name comes up. Again, I think you should just copy and paste my solution because it's very easy to make typos, right? So it's okay to copy. Okay, but if I want to, usually I want to test the size of the things that I have in return. So I want to print x train. Actually, it's going to be underscore x train. Print underscore x test, and then print underscore y train, and then print underscore y test. Okay. Okay. So actually, I don't want to print. I want to print dot shape. Okay. So usually I want to inspect that the shape makes sense. Okay. Again, you can kind of think about this. Okay. So first we have the training data. Okay. X in x. So x always going to have 10 columns. So this one is expected. And for y data, it's always going to have 1 column. So it's good, right? But then in the terms of numbers of rows, so that will be due to the split. So you have 443 rows, and I guess 70% of that is 309. So you have for x train and y train, you have 309 rows, okay? And for test data, you have 133 rows. I guess I'm taking you can take my word for it that this is 70 and 30% split between test and train data, between train and test data. Okay. Again, kind of interestingly, you know, when I first I start with scikit-learn, and I use these functions all the time, right? So when I moved to PyTorch, I was looking for the function or the methods to do similar things in PyTorch, but apparently nothing in PyTorch can do something like this, which is kind of amazing because I'm a little bit confused because I thought that people want to do this, but you know, PyTorch itself doesn't offer this type of functionality, so you have to kind of borrow it from scikit-learn. And you know, like when I look into other people's code on the internet, they're always going to use scikit-learn this function too. So it's kind of interesting why I don't know why PyTorch didn't actually offer this feature, because it's so basic and so it's used all the time. Okay. All right. So we split the data, right? The next stop is we're going to scale the data, and this is the comes back from the box plot that I show you right here. Okay, so right now the data is too further apart in scale, and you don't want that to happen. Okay, so I'm going to scale the data. And in order to do that, I'm going to also borrow another thing from scikit-learn. And again, PyTorch doesn't really offer this type of functionality. Like it does, but in a more primitive way. Like you have to do more. But if you just want to scale your data, people still use this functionality from scikit-learn. It's called the standard scaler. Okay, so the standard scaler is a way to make sure that all of your x have the same mean around 0 and have about standard deviation of around 1. As you can see that once I scale my data, it's going to look, the box plot is going to look pretty much the same width and then center around 0. Okay, so that's my goal here. Okay. All right, so in order to do that, you're going to have to kind of trust me on the syntax because it's not standard. Again, you just have to read the documentation for scikit-learn. But then I didn't go through scikit-learn at all, so just take my word for it. Okay. So the first thing is we're going to do standard scaler, which is a class. So this is a class, okay? So I have to instantiate the class to get the object from the class. So instance of it is going to be called scx, okay? So I need the object that can scale my x. So I'm going to call it scx, okay? And then I'm going to go through my transformation where I'm going to say scx.fit, okay? And this fit function is actually just go through, just look into your data and then figure out, what is the scaling factor that you need for each of the columns, okay? So I'm going to say x train, okay? Actually, I'm going to make it even more concise by do fit and transform. Okay, so that would be fit the data and then transform the data for me. So underscore x train, okay? All right, so I hope that this one, you have tried this, but in the software with Ajahn Vimalin. I think that, the software that you use should have similar functionality, like scaling the data, right? But this one, we just do it in Python. So I hope that kind of ring a bell a little bit, okay? If not, yeah, you should scale your data. There's no reason not to, okay? All right, so I'm going to say this one is my scale train data. So I'm going to name it x train. Okay? And you can start to see the way, the convention that I have for me. Okay, this is for me. I came up with this myself. It's kind of useful because right now I have x train underscore and I have x train without underscore, the leading underscore. And this one distinguishes between the variable that is scaled or unscaled. So the unscaled variable is going to have the leading underscore. And this is a way for me to not lose track of the name. Okay? And this happens very easily. If you just name your variable with, like a random things, you can use the wrong one. You will see. okay? But right now, when I see X train, I know that this one is already scaled. So it's something to kind of double check for me, okay? Okay, so I'm going to scale the other one because we're going to need it subsequently. We don't need it now, which is a test data. I'm going to scale my test data, so scx dot transform, okay? And then x test, okay? And then this one is going to be equal to x test, okay? Again, notice my convention where the variable that is unscaled is going to have the leading underscore, and this one scale, so no leading underscore, okay? Another thing to take a note is that when I use the transformation for the trained data, I actually fit and transform, okay? But when I transform the test data, I only transform it, I don't fit, okay? The difference between these two methods is that your trained data is something that you can learn from it, so you can fit with it. Fit meaning you can learn from it, but then your test data is something that I would recommend you think about it as something from the future. So you don't have access to your test data right now, right? But you just have it because this is because of the way that you split the data, right? So I only transform the data, but I don't fit to it. Fit meaning I can learn from it. I cannot learn from my test data. That's kind of like the golden rule in machine learning. Okay? If you learn from your test data, you are biasing. Your process is biased. Okay. Okay. But the thing that you might not do when you learn with Ajahn Vimalin is you might not scale your Y data. But in neural nets, actually scaling the Y data helps a lot too. And this is due to the way of your activation function. So I would recommend also scaling your Y data, even though that might not be necessary for classical machine learning. So I'm going to do scy equal another object instantiation from the standard scalar class. Okay, I need two objects, one for x, one for y. Okay, and I'm going to go through the same process where the scy dot fit and transform. I can fit and transform my trained data, which is going to be underscore y, right? So y equal, okay. But then this is going to be y train, okay. But then I cannot fit to my test data ever. That's a golden rule, okay. So I can only transform my also not y. I have to do y train, okay. This one's very easy to make mistakes, okay. Test. Okay. And that's going to be y test. Right. So I guess my reasoning for naming things like this is that I will be using the scale data a lot. So I want the scale data to be nice and easy to look at. So I can live with my unscaled data having like a weird leading underscore like this. Okay. All right. So let's check it out to, okay, transform, I misspelled, transform, okay, nope, okay, transform, okay, done, okay. But you don't see the actual value, right? So let's plot it out, okay. I want to plot it to check whether it's actually transformed for real, okay. I can do that by just do this. I can put this data back into the data frame and then do the box plot on it. So this is pretty convenient. So pd.dataFrame, and then I want to put data equal x train, right? And then dot box plot. Okay. So again, the data is already in NumPy array. So I cannot box plot on it. So I'm putting my x train data back into Panda data frame and then just calling the method right away. That's a very easy way to just take a look and, take a look at this data. This is all nice and good. Okay, so again, when you do the standardization on your data, they're all going to have pretty much the same width, right? Although there might be outlier, it's okay. But then they're all centered around 0, 2. That's another thing. Okay. So we're good, right? We have gone through scaling the data. And actually, you can take my word for it. The Y data is already scaled too. okay? So that will be very good for neural nets training, okay? Next up, I'm going to go to building or choose the model, or building the model, whatever you want to call it. Okay. So this is where PyTorch come in. Wait, am I done? Actually, I'm not done yet. Okay. There's one more thing I need to do. Okay. So my data is NumPy array, but if I want to use this one for neural nets training using PyTorch, I need to convert all of this into PyTorch tensor. Okay, why do we need to do that? PyTorch allows us to calculate the gradients automatically. So autograds, right? That's kind of the crux of why we're using PyTorch. So we need to convert all of this into PyTorch first. And that's going to be using torch.num from NumPy methods. Okay, so this one is a bit long and prone to error. So let me just copy this one. Okay, I don't want to type this one because I always confuse like train, test. Usually I make mistakes. So let me just copy it. So you should copy this one too. Okay, like you have to be careful. Okay, on what you are naming things too. Okay, so make sure it's the same, kind of like it's consistent. Okay. Again, right now I also input another underscore pt. Just to make sure that I know that xtrain underscore pt is the PyTorch tensor. So I'm going to use this variable when I actually interface or start training my model. Okay, I'm not going to be using this one anymore. Okay, I'm going to use this guy, right? Okay. So next up, we are going to build model using PyTorch, and that's come from pretty much from last time. Okay. So first thing that I like to do is I like to set the number of input and output as the variable so that I don't have to rewrite my class all the time when I change my data. So first I'm going to say num feature. So what is the number of my feature? Here it would be 10. Or 11, I think it's 11, or 10, I'm not sure, num feature. Equal, okay, and this one, I want to get the number of columns, so I can get it from multiple data. I just choose the one, this one, x.shape, okay. Doesn't really matter, so, with it, if it's going to be train or test or scale or unscale, so this one, I just want to get, give me an x, I want to see how many columns you have. So shape 1, that will give me the column of my features, number of features, and then number of output, okay, that's going to be y.shape1, okay. Okay, so let's check it out whether this makes sense to you or not. So if I print num features and then num outputs, you're going to see that that's going to be 10 and 1. Okay, so 10 columns and 1 y, okay. So 10 x's and then 1 y. So your neural net for this particular data is going to have 10 input and go out into 1 output. Okay, for per observation, mind you. Okay, so the next step is I'm going to build a model now. Okay, so PyTorch model starts with class. Okay, my model, and then I have to subclass. So inherit the methods from nn.module. Okay. Did you ever wonder where this come from? It's come from last time. Okay. This is exactly like last time. Okay. So first I'm going to do the initialization. So init, that's the constructor that takes in self for the first argument. The rest can be your custom input when you initialize your objects. So I want the num features and num output to be my arguments when I create a new class or new model. Okay. So in here, you have to, so this is compulsory. Okay. So you have to call the superclass constructor, and for consistency, this is PyTorch thing recommended by the library. So I have to do it. So super, my model, call the parents class or superclass, and then I'm going to access the init, which is the constructor class of my parents class, and then call it. Okay, so this one, just make sure that you do it, that's all. Okay, that doesn't really matter. I mean, that you don't need to know what's going on inside, although you can look it up if you want. Okay. Okay, so but the rest is something that I need to design myself. Okay, so first I want to do the linear layer. So I'm going to call it FC1, fully connected 1. Okay, that's going to be equal to the linear transformation. So nn.linear. Okay, and in here I need to tell whether what is my input and output from this particular layer. So that's going to be num feature. So taking the input from outside, right? And then it's going to go to 24. And that 24 is something that you can change by yourself, okay? So self.fc2 is another linear layer, so nn.linear, okay? And this one's going to take 24 and then go to 12. Again, by design, but you have to make sure that it's actually the same number, like here, okay? Self.fc3 equal nn.linear, and this one going to go from 12 to 6, if I don't mistaken, nope. And then fc4, so that's going to be my output layer, so nn.linear. But now it's going to be from 6, but then I want to go out to num output. Okay, not num feature, num output. Okay. So when I construct it like this, it's more flexible. You know, I don't really hard code the number of 10 and 1 because that can change due to my data. So I want my model to work regardless of, you know, what kind of data you have. So that's my recommended way to build models. Okay? And then what you need in order to do the forward pass, it's called, I guess, self-explanatory forward, because that's the forward pass. Okay. Okay, so that's going to be the class method. So you get access to self, and then your input, which is x. You can name this one anything. It doesn't really matter. Okay, so I'm going to say x going to be equal to the self.fc1. So first, the first transformation, which goes from, that will be 10 to 24. Okay, I guess I need to input x into it. Okay, again, after linear transformation, it's almost going to be always followed by the nonlinear process. That's going to, oh, I forgot, how can I forget the nonlinear part, the ReLU, okay? So self.ReLU, okay? So that's going to be my nonlinear or activation function. So nn.ReLU, okay? So after I got the results from my linear transformation, it's always going to be followed by the nonlinear or activation function. So self.ReLU, and then you insert whatever you get out from SC1. Okay, and the next step is you can just copy, because this is kind of like the building blocks, right? We do linear transformation followed by the activation function for I would say 3 times. Okay, so 1, 2, 3, basically. So 1, 2, 3. Okay, like that. But then the fourth one is a bit different, because the fourth one is the output layer. So we don't really use the activation function at the output layer. So we're going to self.fc4 x. Yep. Okay, and then I will just return x. Okay, and that would be my, I guess, simple multiple MLP, basically. Okay, some people call artificial neural network. Okay. Okay. So once you're done with this, you can experiment with the model, by meaning that you can create the model. So create an object from this class. Okay. So I can do that too. Let me show you. Okay. So I'm going to say my model, and then I can do the parentheses like this. So this is how you instantiate the model from the class. Okay. Again, but if I were to run this, it will just yell at me. Okay. It yells at me because num feature and num output is missing. Okay. I need to give it, you know, the input and output number. So why don't I just do that? And I already got it here. Okay. intentionally name the same thing. Okay, so num feature and num output, which is tens and one. So I'm going to say num feature equal num feature. Oh, not num output, num feature. Okay, that will be 10. And then num output equal num output. So that will be 1. Okay, and then if I execute the line, then you can see that the output is actually, you know, PyTorch model. Okay, and I'm going to store this model into my variable called model. Okay, something like that, and I can run it too. Okay. So last time we went through some of the techniques to investigate or to inspect the model. So let's do that. Something that you can do right away is to use the torch info and then the function called the summary. Okay, so let's do that. I'm going to copy this one. So summary function. I can summary my model. Just show the summarized information about my model. So model, okay? And then you have to give the input size. So what kind of input do you want to give? Okay, so I want to give my input, so it has to be similar to how you construct your model. So your model has number of input, which is 10, right? And it's output 1. It doesn't matter with it's in terms of the 1, but I want to, let's say my data have, 30 rows, right? And then it has 10 columns. So that will be something that you can use for this particular model. If you say 100, that's okay too. Okay, this number doesn't really matter. It's just the number of rows, right? But what matters is actually this number right here, 10. So it has to be 10 because when you construct your model, you specify that the number of input is going to be 10, and that's important. Okay. So if I do this, then you can see that I can inspect my model, especially the parameter. So this will be a rather light model. It's actually not that difficult to train. It's actually not that long to train. And you can kind of inspect the output, right? Because if you input something with 100 rows, right, it should output 100 rows for you. Usually your model does not change the number of rows because the row is like an observation or the things that you want to predict, right? But then what it's going to change is actually the column. So when you input 10 column, your columns kind of change, from 24 to 12 to 6 to 1. And that number comes from your choice in how you specify this linear transformation right here. Okay. Okay, so that would be, something to look at, and also just take a look at the number of megabytes. So this one, not that much. Okay, you should be fine. Okay. Okay. As of now, we are right here. So we just show us the model. Okay. So the next big thing that we're going to do today is called training the model. Okay. So this is where the back propagation is going to come into effect. Although behind the scene though. Okay. PyTorch can abstract all of that for you. All you need to do is just tell it to keep doing it. That's all. Okay. So for here, I'm going to create another cell, and I'm going to start training the model. Okay. The first thing that you're going to do is, I think you should experiment with how you would train your model once. Like usually you have to do it a lot of times, right? But how you would do it once first. And then you can kind of improve your algorithm to do it multiple times. Okay, so how do I learn once? Okay, to do that, you need the following. You need the optimizer. Okay, the optimizer is is how you would update your weight and biases. That's called the optimizer. If I were to relate back to where we were in our lecture, I think that might be a good way to connect to what we did last time or what we learned last time. Okay, right here. Okay, I'm looking for we went through a lot of things, but in the end, you remember this part, okay? Updates the parameter. Okay, so that is something that the optimizer will do for you. Okay, so behind the hood, behind the scene, the optimizer is going to take the gradient and updates the weight for you. Okay, that's the job of optimizer. And I think I have some basic information about the optimizer. Should be here. Okay, so the most basic thing you can do, which is the equation that I just mentioned a little bit earlier, that would be called stochastic gradient descent. Okay, so that would be the most, I guess, classical way, but nobody uses that nowadays. So I guess for a more recent iteration, you do adaptive moment estimation or ADAMS. Okay, again, there are many newer things now, but we're gonna stick to the kind of like the classic standard. Okay, so ADAMS. Okay, again, so think about ADAMS. The ADAMS job is to update the weights and biases for you. Okay, so that's all it's doing. So I'm gonna have to set up the optimizer. Okay, optimizer. Okay, equal to. Okay, so this one you have to check the documentation. Okay, how you would instantiate ADAM. So again, in Python, everything is the class. Okay, so if you want something like optimizer come from class instantiation. Okay, so torch dot optim dot adam. Again, this is the class, right? Your optimizer will be the object. Okay. Again, in here I have some options to input as an input I guess input argument into the constructor. Okay, and it's pretty much required to do this. So I have to give it model dot parameters. Okay, so what does model parameter do? Let me show you. Model parameter. Okay, it gives you a generator objects. Okay, so this object is gonna give the weights and biases. Okay, in sequence to whatever's calling it. So right now I'm giving, okay, take my generator of my parameter, okay? And this ADAM thing or optimizer will, update the weights and biases in sequence in my model. Okay, so think about the fact that now my optimizer have control over what the value of this is going to be. Yeah, that's how you would want to think about it. It's actually linked, like this thing is actually linked to this one right now. And this one can change the weight and biases in my model. Okay. Another variable argument that you might want is the learning rate, because learning rate is a super important parameter when working with any optimizers. Okay. The learning rate in a nutshell is this part over here, this guy over here. Okay. That learning rate tells you how fast or how much your weight is going to update every time. And if the learning rate is too high, your model can become unstable, right? You need to keep learning rate low, but if it make it too low, then your model will never get trained. It will be too slow. Okay, so it's a balance between stability and computational expense. Okay, so I will keep my learning rate, relatively low, so 0.01. So usually this one, the value or the magnitudes come from experience. There is not really a way to officially or theoretically estimate this one. You just like from experience, usually. So something around, less than 1 would be a good start, okay? Okay. Let's check out. The next thing is I'm going to actually start training the model. Okay. So first we'll put the model in the training mode. So model.train. Okay. And this one change a lot of things inside. Optimize for training. For example, set out the weights into the gradient mode or something. So start tracking gradient basically. Model.train. Okay. The next thing is model dot, I want to do optimizer dot zero grad, okay? So this one is going to reset the gradient. So optimizer actually can have non-zero gradient when you start it with. So it's always a good idea to always kind of clear everything before you start your forward pass to keep track of the gradient. So make sure the gradient is all 0, okay? The next thing is I'm going to perform the forward pass, okay? So this is actually similar to how you would do in our lecture, okay? Because I was saying that, okay, in order to do anything in here, we're going to start with prediction, right? We're going to start with prediction with the wrong weights and biases. Like the weights and biases, it's just random things. It's okay, it can be random, right? And then you're going to go for the forward pass. So this path like this, go to the right, right? That's the part where they do it here. So during the forward pass, PyTorch is going to start collecting all the gradients. That's the part where it's actually very, very useful, okay? So in our example, I have to calculate the gradient myself, right? I have to do all of this, like all of this, right? All of that, right? But for in PyTorch operation, actually all of this is not calculating during the backward propagation. It's actually already calculated during the forward pass, like all this value. So this is why we need to do model prediction first, okay? So I'm going to do model. I am going to predict with the X train, okay? I input X into it, I expect the Y to be an output, right? So I'm going to keep this variable called Y predict. Okay, so think about this, it's the forward pass in our lecture, same thing. But PyTorch collects all the gradients, store all the gradients in memory, okay? All right, so next up, what do we do? After we do the forward pass, after we do all of this, what we did is we are calculating, where is it? Hold on, right here. Okay, so once we did all the forward pass, right, check this out. The next thing is we calculate the loss, right? This is exactly the same process as we did it here. So forward pass, what is your loss, right? So we need the loss function, okay? Again, the loss function is another object that you can instantiate from the class. So I'm going to say loss function equal, and here again you need to look it up of which class you want to use. So I want mn.msc. That's going to be the mean squared error, which is exactly the same as this one over here. Same thing. Okay, you are calculating the loss. Okay. So down here, I want to calculate my loss. So loss equal, okay, loss function. And then I want to input the Y predict and also the ground truth, which is Y test, Y train, sorry, Y predict and Y train, okay? And I have to use Y, actually I need to use X train PT because this is PyTorch, okay? I might have forgotten to use, I'm not sure, in my, I use it in my example too, yeah, that's true. Okay, so actually I forgot, this is important, okay, because you need PyTorch tensor in order to keep track of all the gradients. So it probably will not work if you forgot this. Okay, all right. So next up, what do we do? After we calculate the loss, we do backward propagation. Okay, so we're going to do it here too. So the way to do it is we're gonna calculate loss dot backward like that. Okay, again, it's kind of seems weird, right? So like which one would you call the function from? But I want you to kind of think about it, that the way that PyTorch store the variable is they store everything in the same place. They never copy anything. So if you input this Y predict into your loss also have access to all the gradients that the model is calculated. The same thing with when you do optimizer. Like when you put all of this in, your optimizer also share the same weights as your model. So everything is all connected because PyTorch is very, very good at optimizing and not creating the copy of anything, because that's kind of important for memory management. Okay, so when I say loss.backward, it's actually kind of going through the model and do the back propagation on the model itself. Okay. All right. So once we did all the propagation, what happened is that it's going to update the I guess the gradient, right? And then once it updates all the gradient, we can start updating our weights and biases. So that's going to come from the optimizer, optimizer.step. Okay, so optimizer.step means that we are going to update the weight once. Okay, and again, this part, optimizer have access to the model's weights and biases. So you can call this step from the optimizer, not from the model. Okay, and there you go. This is done. This is how you would train your model once. Okay, so let me just go through it here. See, it runs. Although it might take some time to initialize things, but you know, this is how you would train your model once. It takes a bit longer than I thought, but I'm wondering why. I thought one step would be, you know, instant. Oh, there's oh, okay, MSE loss. Sorry, I misspelled it here, right? MSE loss. Yeah, wrong loss function. Okay, try again. Yeah, it should be quick. You know, it should not be that long. Okay, right? So I can run the whole files again, just kind of make sure that everything's correct. Okay. All right. So if you see, I mean, after this, you know, I challenge you. Okay, if you want, you can look into any other PyTorch code. You're going to see the same thing. You're going to see this one all the time. I think you have all the knowledge you need to actually read people's code now. Okay, although, I mean, to give people some credit, like, this is just the basic building block of how you train once, right? But it doesn't really give you, first, you usually train the model more than once. Second, you need to keep track of, you know, your progress, right? You need to be able to stop whenever you want, like, or stop whenever some condition is met. So that's why when you see other people's code, it's going to look more complicated because there are other things that they need to do in order to train your model. But in the core, but at the basis of everything, it's just this line over here. That's all. That's how everybody do it nowadays. Okay. All right. So I'm going to start adding more things in here because we actually need more things in here, even for the simple example like this. Okay. First is I want to train this thing more than one time. Okay. When I say more than one time, meaning that, you know, I give the model this much data, which is 443 rows, okay? Once I give the model 443 rows, we usually call this step one epoch, okay? That's the word epoch in here, okay? E-P-O-C-H. That means that using all the rows, okay, once, this is called one epoch. So I want to go through my data multiple times, multiple rounds of data. So I will just have to do multiple epochs, okay? And for that, I'm going to say n epoch. So I can specify how many rounds do I want to go through my data and update the weights, okay? So let's say something like 100, right? And then you need to loop this process now, okay? So I'm going to go for 4 epoch in range of n epoch, okay? And everything in here need to be inside the for loop code block. Okay? Again, this is all I need to do in order to train multiple times because training one time never going to work, right? You have to do multiple times. So let's try it out. There you go, 100 times. Okay, it's pretty fast, right? So let's try 1,000 times. Why not? Yeah, definitely a little bit longer. So you can kind of see how long your model takes, right? Usually this is like a good way for you to first start using your model. Like even for me, sometimes if I see really complicated model, I just want to peel it apart and just see if what happened if I just train it once. Like how long does it take? If my loss is going down, we'll go through that later. Okay, right? So right now, actually, this is the problem now because I train my model 1,000 times, but I don't know if that is actually enough or not. Okay, in order to determine whether this is good or not, you have to look at the loss value. The loss value is whatever you calculate, every time after you train your model. For example, in our example, our loss goes from 7 to, our loss goes from 5 to 0.352. See, from just one pass, right? I can reduce my loss a lot, right? But then what happens if I were to do it again? Then I expect my loss to keep going down. Okay, so that's how I would kind of monitor my training progress, my training process, okay? So in order to do that, I need to actually keep the loss somewhere, okay? So first I need to say loss array because I want to keep it in an array just for visualization purpose and tracking purposes, okay? And then I want to extract the loss value out, okay? And for that, I want to say loss.item, okay? So that would be a way to extract what is the loss in for the current epoch, right? And I want to store it in my loss function, append. So if you have Python list, you can append it like this, okay? Something like that, okay? Or actually in my code, I separate it into a variable called epoch train loss, which is fine, loss.item, okay? And this one is epoch train loss, okay, something like that, okay? And there you go, we're done. So let me run again one more time. Nope, there's something wrong in here because loss function, oh, not loss function, but loss array, sorry. Wrong variable, okay. There you go, done, okay. So let's see how we were doing in terms of loss. So for here, I would like to use my favorite visualization library called Seaborn SNS.line-plot. I'm going to input my loss array into it. And you can see right away that, wow, it's not too bad, huh? And what you're looking for is, should go down. This is your loss, right? It should go down. Second of all, it should plateau. Okay? If it's not plateauing, meaning that you can train more to make your model even better. Okay? So why don't we just do it more? I'm going to do it 2,000. And of course, it's going to get longer, right? I think 2,000 is good enough. Although if you really want to like squeeze out all the juice from your data, then maybe you can do more, okay? So it doesn't matter, right? But this is another thing that you need to do now. You're going to keep the loss array, okay? A loss in an array, okay? And the last thing that I want to do is, but then what is actually my expected model performance when I actually use this in the real world, right? Right now, my loss is super low. And that's kind of expected because if you're training your model is actually adapting to your training data. So your loss is of course it's going to go down, right? But then then we are wondering what your model performance would be once it sees the data that it has not seen before. And that is the job for the test data. Okay, so now we're back to, I believe, the last step in my stuff, which is predicting the results. Okay, so we need to predict the performance from the test data. And you're going to see that even though your training loss goes to 0, your test loss is going to be non-zero, always, okay? Because that's the unfortunate truth, okay? Okay, let's take it out. So in order for me to calculate the test data, I can also do model and then do, you know what, y test PyTorch. That will work. Oh, okay, actually does not work because this one is X train. It will work, right? But check this one out. It actually has gradient attached to my data, meaning that even though I just want to get the values out, it's actually tracking my gradient, which is kind of waste of computation. I don't want this to happen, right? And there are ways to do that kind of recommended way. So if you don't want your model to start tracking your computation, because this one is a prediction mode, you can put all of this into your with torch.nograd block, okay? All right, so again, this syntax probably is going to be unfamiliar to you, but when you do with something, this one is called the context in Python. The context in Python is kind of like the separated environment for you to do something extra, okay? For example, when you want to write something to the file, you will actually use with the opening of the file. So that's the context for writing things to the file and things like that. So you will see with in some special case when you start to use Python more, it's called the context. Okay, but regardless of that, if I were to run this again, and then I would just say print, right? I want to print this thing out. You will see that no grad, because when you with torch.nn no grad, there's no gradient tracking. That's why the output is just a number. It's not tracking by gradients. Okay, okay, that's a small point, right? You might think of, I don't really care if it's tracking or not track, right? But then once you start to work with large model, any computational gain you can have, it's useful to do. Okay, so that's why people do it. Okay, so I want to get this one to be my test predict. Okay, so my y prediction from the test data, and I want to calculate the final loss. So final loss. Okay, that's going to be equal to loss function again. Test predict and then y test pt. Okay, so again, my loss function is not tracking the gradient too, so that's a good thing. Sometimes it can take a long time if you need to track the gradient from the loss function. Okay, so let's see what I have in the end. I'm going to print my final loss, okay, and check this one out. I'm going to run one more time. 2.5, okay? How is that compared to the test on the train loss, okay? Your train loss goes down to, almost 0, right? But your test loss is still there at 2.5. And that's something that you need to keep in mind, that is this something that you want? If you want something to be lower, you got to do something about your model, like optimizing the hyperparameter, or you have to do it again. Train more. There are many ways you can do. But I want, before we end this session, I want you to see the behavior here, because every time you run the model, the loss is different, okay? And this is kind of the thing that's quite a headache for neural nets, because when you initialize the model, the weight initialization is different. And the training step is going to be different, right? All the updates can be different. And your model performance is going to differ too, okay? So as you can see right away, even if I'm training this for many times, I still have a lot of a variation in my loss, right? So what people typically do is you have to calculate it multiple times, and you can make an average, you can do a box plot to see kind of like how much is the range, possible range of the loss that you're expecting. Okay, so one value is usually not enough, okay? But for this class, that will be okay. But I just want to tell you that there are, subtle things about working with neural nets that, it's kind of headaches a little bit. Like this thing, it doesn't matter that much in classical machine learning. You usually get pretty consistent results, but neural nets can be pretty vary like this. Okay, I'll give you